Next up, we have Graeme Burt, who is going to give us a talk all about the UK's contribution to the high luminosity LHC project.
Hi there. As Dan says, I'm going to tell you a bit about some of the stuff we're doing for High Lumi, which is a project which is pretty much dominated by engineers rather than physicists, which is quite interesting. So this is the LHC current plan. We're currently in the start of run 2. We're about to have a year-end technical stop in 2018. Then we have a long shutdown after that in 2019. And then by 2022, the LHC is running at its full energy, full current, full luminosity, which is the number of collisions. But this level of collision, they'll have about 300 femtobar inverse femtobars of data, isn't enough to discover everything they want to. They're now looking for some very rare processes, and to see rare processes you need a lot of data. And at the current data rate, it would take almost 50 years to make some of those rare discoveries. So the physicists want more data much faster. And the High Lumi project is to try and address that. So the detectors are also limited, but they're going to be upgraded at the same time. So this is the luminosity as a function of year. You can see that we want to go from about a specific luminosity of 2 times 10 to the 34 to about 5 times 10 to the 34. We think we can go even a bit higher than that, maybe up to 7 times 10 to the 34. But how do we make this big jump from this level to this level in terms of collisions? It's quite a big jump. You can't make small incremental changes. We need to make some large changes to the accelerator and the way it works. So the simplest way of doing it is you pinch the beam down, so you have a very small area. You've got a bunch which is made up of very small protons, and when you collide the bunches together, you have trillions of protons in the bunch, but typically we only get maybe 20 collisions per crossing. So the cross section, the chance of any proton hitting any other proton is actually really, really low. So if we can push it into a smaller area, then there is more chance of them colliding. If you have the same number of protons in the same area and they pass through each other, there is more chance of them hitting each other. At the moment, with the current LHC magnet set up, we can get to about beta stars a measure of the beam size. You multiply this by the emittance and you get the beam size, which you square root it. So they get down to what's known as beta star is 40 centimeters, which is a micron size beam, tens of microns. But they would like to go smaller than that. And to do that, you need to upgrade the magnets, the inner quadrupole triplet, and a new dipole to get a very fine beam. And they've done some measurements, and we think we can get down to maybe a third of this value. There is a problem, but when you make the beam smaller, the beam becomes more and more sensitive to what's known as beam-beam interactions. The beam itself is a bunch of protons, and when they collide, after they collide, they're coming out. The spent beam will pass by an incoming beam. They will see each other, and their fields, they will repel each other, and you will get a perturbation to the beam caused by the electric field of the outgoing bunch. And this is called a beam-beam effect. And the way you get around this is by you go to a bigger crossing angle. So this is the head-on case. This doesn't work because the outcoming beam would hit the incoming beam. So you add a crossing angle so that they become separated. And we need to go to a very large crossing angle for the LHC. But as you can see with a crossing angle, you don't get this perfect overlap of the bunches. You only overlap a small area. So the advantage you've got of going to a small beam, that you get them all compressed together, actually goes the other way, and you actually get less collisions. So to fix that, you need to collide at a crossing angle, but you need to rotate the bunch round so that the beam travels sort of sideways, and you still get the full overlap with the crossing angle. And this is the current LHC. The red line, that's our luminosity. The green line is what we would do if we pinched the beam down and kept it head on, but obviously that's not feasible. This is, and the blue and pink line is what we do if we rotate the beam. So it's very close to the perfect case, and this is if we didn't rotate the beam. So you can see there's maybe a factor of 3 or 4 addition in the number of collisions by rotating the beam. How do we do that? Well, this is where the engineering comes in. So you get an RF cavity, but the RF cavity doesn't point in the direction of the beam, it points upwards, or left or right, depending where you want to rotate it, in the horizontal or the vertical plane. We do both in LHC, depending on the exact detector we're using. So the beam comes in straight, comes to this RF cavity that's turned round. It then kicks the beam sideways, but because it's an RF, it's varying with time, and we have it set up so the front of the beam gets kicked up and the back of the beam gets kicked down. It rotates towards the interaction point, collides head on. The magnets then refocus the beam to go back on axis, and then we push it through another RF cavity that takes the momentum off the beam, and it can go straight ahead. Sounds simple enough, but it's actually really difficult. There's lots of upgrades needed. First of all, we need to change the, we'll start down here, we need to change the quadrupoles to focus. We need to change the collimation in there because the beam becomes more, as we pinch the beam down, it becomes more sensitive to the beam halo. We need to clear that off. So what we have is the bits of the beam that aren't part of the main beam, they're going to need to be stripped off. So we do that by having some big jaws that come into the beam and they slice off the beam. So we need to improve them. We need to add crab cavities, which are going to do rotation, and various other stuff. Power supply upgrades are needed. In total, it's about 1.2 kilometres of the LHC needs to be ripped out and reinstalled. So it actually makes it the biggest particle physics machine in construction at the moment. It's not just interaction regions, that 1.2 kilometres, the work's needed all round the ring. So we need new diagnostics everywhere. We're rotating this bunch about, we need to be able to measure that. We're going to go to a higher current as well to get more collisions, and we need detectors that can handle that kind of current. So we're going to a gas jet monitor of the beam rather than, at the moment you use screens, we're going to go to gas jets, which will be more tolerant. The power supplies themselves, well, they're going to get fried by the increased radiation dose when we go to a higher current beam. So we need to put those power supplies on the surface, and that needs some links to get the power in there. New collimators everywhere. So it's a whole bunch of stuff that needs to be put in the machine to fix it. So as I say, it's going to be the largest high energy physics accelerator in construction at the moment with quite a bit of changes. So in the interaction region, we're changing the quadrupoles. We're changing some other stuff, but the main thing is the change of the quadrupoles. In the matching section, we're adding crab cavities. That's the new big thing. And in the dispersion section, we're having new collimators, and we're having a dipole that runs up to 11 Tesla, which is higher than we can currently go. So the magnet process, the LHC dipoles currently run at 8.3 Tesla, but we need 11 Tesla. So we've got to have a magnet that runs at a higher magnetic field than that. Now when we built LHC, that was the highest magnetic field that could be generated in the accelerator and dipole configuration. So we have to go beyond what was state of the art then and have a new state of the art that runs at not just 11 Tesla, because it needs to be able to be tested above that, so we're going to aim for 12.3. And the same with the quadrupoles. We need 140 Tesla per meter, and we currently have 70, which is again a 12 Tesla peak versus 8 Tesla peak, but designed for 13.5 Tesla. So we're dealing with very high superconducting magnetic fields to do that. And if you look at the progress in accelerator magnets over time, by the time LHC was sort of designed, we were very close to the niobium titanium limit. When you have a superconductor, the superconductivity works by a weak coupling between electrons inside the metal, and it's a weak coupling. So if you provide too much energy to those electrons, they break apart and you don't get superconductivity anymore. So if you have a high current running through that cable to create a high magnetic field, then what happens is the superconductivity just breaks down and it becomes a normal conductor, and then the magnets don't work. And the limit for the material we use, niobium titanium, is just above 9 Tesla at the moment, and we need 13.5. So you can see we have to go to a completely new technology, niobium 310. And in fact, The first prototype of that has now been tested. The first niobium 3-tin magnet that delivers above niobium titanium performance has been tested at, I think it was at Fermilab. There's a whole bunch of stuff needed. Various magnets about the machine need to be done, and this is mostly being handled by the LHC America Research Programme. So that's the American Particle Physics Lab are making an in-kind contribution to the project, and they're mostly handling the magnets with a bit on crab cavities. It's a new regime for LHC. As Dave said, the LHC doesn't normally work. CERN doesn't normally work with in-kind contributions, and it's quite difficult to do. LHC is now trying to move to that sort of configuration. So all the things that David said could go wrong, CERN are going to try and do them wrong as well. So you see we've got, these are just the cryo modules. There's a lot of stuff, components needed, but just mostly the magnet and the RF cryo modules. You can see we've got American, Spanish, Italian, Japanese, French, British, and CERN cryo modules. Quite a lot of in-kind effort on very complex cryogenic systems, which is quite important in the system. We haven't actually declared right now the UK will provide an in-kind contribution to the final project. Right now our in-kind contribution is building prototype cryo modules, the pre-series one. We'd like to hope that we will build the final cryo module, but there is no agreement for us to do that at present. So High-Lum LHC UK is a project that was launched on the 1st of April this year, and it's about the UK making key components for the LHC, or at least doing the pre-series of these key components, with the anticipation that we would make a bid to STFC in 4 years' time to do the series production as well. It's split into 4 areas. Work package 1 is the collimators, which has got 2 tasks in it, one of which is simulation of collimators, which is the physicist, and then we have some engineers from Huddersfield who are doing the building of actively aligned collimators, where they measure the beam position and they move the collimator in real time to react to that using sensors. So nice engineering project. Again, with the crab cavities, we have a work package where we're looking at simulations of the crab cavities, and then we have the real engineering project where we're both testing the superconducting cavities that are made by the US, and we're building the pre-series cryo module in the UK at Daresbury Laboratories. Then we have the diagnostics, where we're making 2 diagnostics for the machine. We're making an electro-optic BPM. It's like a normal BPM, but it's using very high frequencies, because if you go to very high frequencies, you can have a very high bandwidth. And if you have a very high bandwidth, you get very good time resolution. So because we've got this rotation of the bunch, we don't want to measure the average offset of the bunch. We want to know how the head of the bunch is offset compared to the back of the bunch, and that needs a high bandwidth. So we're using an electro-optic system for that, and a gas jet beam profile monitor, where the beam goes through the gas jet, ionizes some of the gas, and by measuring those ions, you can get a measure of the beam profile. And finally, we have the superconducting links, which is what links the magnets to the power supplies when we move the power supplies to the surface. At the moment, we've got huge currents flowing through these, and they're right next to the magnets. But in the High-Lum LHC area, the radiation damage will be so high, these magnets won't last, these power supplies won't last very long. So they need to be moved to the surface, and superconducting links is the way to go to handle high powers for long distances. So I'll take you through each of those 4 work packages in a bit more detail. So first of all, I'm going to spend the most amount of time on the crab cavities, because A, that's my area, and B, it's where the most engineering effort is and less physics effort. So this is the LHC. There's 2 main detectors, CMS and Atlas. There's also LHCb and Alice. They are not being upgraded. It's only Atlas and CMS, the general purpose detectors, which will be upgraded as part of the LHC upgrade project. We're going to put crab cavities at this entrance and exit to both of these detectors. They'll be in cryo modules. This is an old slide. Originally, we were going to put all the cavities in one cryo module. For reasons of timescale and risk, because we've tested 2 cavity cryo modules, we're just going to carry on and use 2 cavity cryo modules in the LHC, with 4 2 cavity cryo modules on each interaction point. So this started off years ago, I can't remember exactly when, but 2009 I think, where the problem is if you take a traditional deflecting cavity and you put it in LHC, because the bunch length is so long, 8 centimetres, you can't use a cavity which has a higher frequency than 400 megahertz without bending the beam into an S-bend shape following the sine wave. If you take a 400 megahertz elliptical deflecting cavity, similar to the KKB cavity, and you put it in the LHC, you find that both beams would have to go through the same cavity because the beam separation is already fixed in the LHC. They designed the LHC not anticipating they would have to add crab cavities at some point. So it's almost impossible to increase that separation. It's too late now. So we've had to make a cavity which fits in the current LHC environment, but which will also work at 400 megahertz. So we had 4 novel designs for this. I'm always remembered when I started working on this project, there was a review of, I think it was Eurotev or one of the early European collaborations, and we had an SRF expert who won't be named who was presenting a review of all the SRF effort done in Europe, and he got to the crab cavities and he just sat and looked at the slide for a minute and goes, well, this is clearly never going to work, which was heartening as a young academic. However, now we have had 3 different systems that have been proposed: a UK design, a JLab stroke ODU design, and a Brookhaven design, and all 3 were shown to reach the design 3 megavolts per metre at a Q of above 10 to the 9. So these are very complex geometries. They looked quite crazy when we first started, but the field of SRF has moved on quite a lot, cleaning techniques and manufacturing techniques, and we've managed to get all 3 to work. By coincidence, all 3 were made by NioWave. This one actually had part of the inside machined rather than pressed. We actually machined niobium from bulk ingot, and that was fairly successful. And the rest are just pressed parts that are e-beam welded together. All right. Oops. So we have the 3 cavities. This was down selected to the 2 American designs by a panel. Unfortunately, our one wasn't selected. But that's okay because that's moved us on to doing the cryo modules, which is a much more interesting project now. So we're taking a lead role in the design of the cryo module for SPS, and we are actually building the cryo module for the pre-series. There's a few components we've done so far. We're leading the thermal and magnetic shields. We've already built the prototype cold magnetic shield. This is using cryo-FE, 1 millimeter thick. The interesting thing about cryo-FE is it's a very good magnetic shield unless you put any stress on it. You bend it at all and it stops being a good shield. So you've got to be very careful with the construction and minimise any stress. And you've got to build it around the cavity, which is actually quite difficult if you don't want to put any stress on it. So it's a very complex design. This is here with some stiffening ribs as well. Also, the CERN people who designed the helium vessel were nice to us and gave us absolutely no clearance between the cavity and the helium vessel. So it had to hug the cavity shape to some degree. We did the cavity supports. We used actually some practice that the Daresbury Mechanical Engineering Group had developed as part of a RAL space physics project. They wanted something that would thermally expand and not put stress on the cavity, but would stiffen it against microphonics. So we came up with this blade design. So the blades will bend in the direction. It's supported by the power coupler, so it will bend in the direction away, radial away from the power coupler, but will be stiff in that direction. And we can see that we were able to push the microphonics up to 19 hertz using this design. Originally it was down at about 10. So we managed to double it using this blade, because initially it was rotating about there. And since then we've added 2 more blades on the side, and we've pushed it back up to above 25 hertz. We've also been looking at the BCP process. Interestingly, everyone knows that the acid etch rate depends on the flow speed of the acid. But how does it depend? Well, no one knows. No one's actually done that measurement. So it's when you've got a complex cavity shape, if you look at the flow of the acid in the cavity as you put it in one port and out another, the flow speed you can see is non-linear across the surface. It varies in different places. So we'll etch some areas more than others, but we want to know how much more it will be etched. So we're also going to do a measurement where we're going to have a pipe of niobium, put different flow speeds through it, and measure the etch rate. So then we'll have a number for how this bit's going to be etched more than that bit, for example. We're also taking a lead on the cavity testing. We're doing the testing of all the Hong couplers, conditioning of the fundamental power couplers. We're measuring the triple R of the cavities. We're doing the bead pools to ensure the cavities have the field we think. And we've also done some mode tracking due to the tuner and due to thermal effects of the higher order modes. Because the higher order modes are also affected by the tuner and any temperature transients. So we want to be able to track that to make sure we don't get any instabilities in the machine. I'll very quickly go through the last 3 tasks, don't worry. I'm going to go through them very quickly. There's the collimation. 2 issues with the collimators. They need to be able to take a lot of damage, but also as the beam passes them, it sees an impedance change and it creates a lot of radiation called wake fields. So we need something that's got a low impedance and can take a big hit. So we need to design that. Now having the movable collimators is quite good because then you can have the beam go through dead centre, so you don't excite any transverse radiation wake fields, you only get the longitudinal type. So that will be part of the project. There's also some physicists doing lots of simulations of that. And we're going to look at new materials as well for these collimators. This isn't our new material, this is one that CERN's looking at, but we're going to be looking at other materials. We're thinking of looking at graphene, potential way of reducing the impedance. For the diagnostics, as I mentioned, we've got 2 ideas. We've got the gas jet, where the beam goes through an area filled with gas. It gets ionised. It's a high pressure gas jet. It gets ionised by the gas jet, and then as they get ionised, because the position of the gas jet depends, the transverse position depends on the longitudinal position, we get a beam profile measurement. And the electro-optic BPM, we pass a laser through a nonlinear crystal. The beam cell field goes through it as well. They mix together, and then because it's nonlinear, that puts an imprint on the laser field. And then by looking at the laser field's imprint, we can work out what the beam's field looks like. And if we know what the beam's field looks like, we know what the beam looks like. Finally, we've got the superconducting links. Now, currently the power supplies are in the tunnel and they're going to get fried, so we need to move them to, originally it was going to be the surface, but we're now digging a separate cavern for them. But either way, it's not going to be near the beam. So we need to have almost a kilometre of wires carrying either 50 kiloamps or 150 kiloamps of current. So it's a lot of current and a lot of distance. Normal copper, that would be quite lossy and would generate heat as well, I guess. So superconducting links is the way to go. And now CERN has built the world's first long, commercially developed superconducting link. So they've got a 20-metre cable using commercial processes. Lots of physicists have done it in the lab and they've like, I have 2 millimetres of this. And they're very impressed with that. But that's not what you need for LHC. So CERN's been looking at taking nothing new, just taking new processes and how you would manufacture 20 metres of this stuff. And then that can be extrapolated up to 700 metres and 300 metres. So there we go. And that works at 25k. And this one handled 1 kiloamp. So not bad. And this was the world record for a high temperature superconductor, real progress, and the actual feasibility as opposed to lab-based demonstrations that the physics groups have been focused on. So in conclusion, the next big high energy physics project will be the LHC luminosity upgrade, which is now in the prototyping phase. Some components are in, there are some tests being done on test stands. In the next 2 to 3 years, we're going to start to see components go into the SPS, which is one of the small accelerators that feeds the LHC, because some of these components have never seen a proton beam before. So we're going to test their work on the SPS before we move them into the LHC. The UK is going to be developing quite a lot of the contributions to that. We're not doing the magnets. That's the US that's doing that. That's the big upgrade. We've picked some very high profile but smaller work packages, which is matched to the amount of resource we think we can get out of the UK government. And that's namely the superconducting links, the crab cavity cryo modules, some of the diagnostics, and the collimators. I think, I hope you have been maybe inspired a wee bit by this. So, any questions?
Any questions for Graeme? I've got a question. What is the total UK contribution then in terms of money?
At the moment, the project is, well, at least what we've done, what we've guaranteed, we'll do the development of the prototypes, is 8 million. 4 million of that is coming from CERN and 4 million of it's coming from STFC. So that's the total expenditure so far. If we go to the next phase, then it could be substantially more. I mean, the cryo module is about £2 million worth of effort. So if we were to deliver all 8 of them, then that's about 16 million that would be needed. But yeah, I'm extrapolating a wee bit there.
Any other questions for Graeme? No? Okay, let's thank Graeme.